Okay, so today we're going to continue with the system boot. We'll boot into main, and then we will start executing inside main. And what we're going to be doing, we're going to be building the kernel page table. So just a quick recap on what was happening last time, right? Remember, we talked about what happens when you enable power in the machine, like a bunch of different software, which we've never heard about, right? Is actually running first before even we get to the bootloader, right? So it was Intel Management Engine, then BIOS. BIOS can enable system management mode, which will keep running there as well forever, even though even after the boot sequence is over. BIOS also enables firmware and various softwares on all the devices in the machine as part of the initialization, right? Then BIOS passes control. BIOS essentially initializes everything and then passes control to the bootloader. And this is still, I wanted to come back here. This is still the C file. Let me maybe go back a little bit here just for the sake of, to recap the world, right? So this is the world in which we're currently running. So we imagine the machine has 512 MBs. That's just an assumption. x86 will be using some fixed number, roughly around 234 megabytes. And this is done to avoid complexity of dynamically querying the ACPI, or essentially a mechanism which allows the operating system to learn dynamically how much physical memory is available on the machine, right? And so what we've done is that this is our bootloader. Inside the bootloader, I was asking, remember I was asking, why is it not in the data section? So, I mean, I have my own theory, but no one came back to me. But I think this is because when we were reserving this space, we actually were reserving space in the text or in the code section, right? So this is just beauty of the assembly, I guess. Assembly itself, compiler would create a new section, right? But in the assembly, you have full flexibility, and you can say, look, just reserve me a couple of bytes, and I'm not going to be using them as code. I'll be using them as something else, and you're using them as GDT, right? So that's why we copied only the text section. And remember, when we copied out from ELF file into the binary, and this binary, which is less than 512 bytes long, was sitting on the disk. This is our bootloader, and then the BIOS loaded it in memory at the address 7C00, jumped to it. We executed a little bit in assembly, set up the code and data segments in the global descriptor table, enabled segmentation, set up the stack, which is growing down. This is this blue thing growing down directly from underneath 7C000, right? And we jump to the main function, to the boot main function, right? After setting up the stack here. And boot main was a C function. And what we were doing here is that we said, look, we will load the kernel at address 1 megabyte, which is this address, right? And we're using this read segment from disk. This is the pointer in memory. So if we said, okay, this is the physical memory starting from 0, and this is our address at first megabyte, which is 10000, right? So this is where ELF is pointing. It's pointer point directly here. So if we first read 4 kilobytes here from disk, right? So it comes from disk, and it's 0 sector of the disk, right? When then we check if it contains an ELF magic. I was confused about this loop, right? But what happens here really is that we say, look, from the ELF, which we read in memory, right? We will take an offset of the program header, right? And we assign it to the program header variable. So essentially, if this is your again memory, and this is the 4 kilobytes which you loaded, 496 bytes, right? So this was your ELF. You really just loaded. This is the ELF header, right? In memory, right? And what you're doing here, you say, look, I will do the offset into the program header table, which contains a couple of entries. So this is the program header, it points right now. And then I will be looping through the program header. For each program header entry, I will take their physical address assigned to PA, right? And I will read a segment from disk into this PA address, right? So, and there might be a case where the size of this section on disk, which is a file size, right, will be smaller than the size of this section in memory, right? So in this case, file size, so for example, if you have a BSS section, right, for example, which got compiled somehow together, right? You say, look, I know that file size is smaller. So on disk, the file is smaller than in memory. So what you do here is that you add, when you loaded the everything from disk in the PA address, right? So this is the physical address. So for example, somewhere here, PA is pointing, you load it in from disk, right? This is the code section of the kernel. But really what you're doing here is you padding everything with zeros to the proper file size, right? So essentially you say, that's simple arithmetic here. You say, I will start from the file size, we'll be using zeros, I will go for the distance between the mem size and file size. This is some delta, and this is the delta, right? So you will fill it in with zeros, right? And then what we've done is that we actually jump to the entry of the kernel, right? So we said, okay, we know that the elf header has an entry pointer. It will be pointing somewhere over here, for example, right? This is an entry. We assign it to a function pointer, and we just simply invoke this function pointer. Are there any questions about how we got to this entry point at the moment? All good? It's somewhat related to the homework which we were currently doing. So essentially very related, right? So that's why it will be easier for you to understand both the lecture and the homework, right? And I was explaining a little bit about what the read seg function is doing. So it's just using in and out ports to communicate with the device, waiting for the device to reply. That's less important right now, right? And this is the very first file of the kernel itself. So if up until now, we were inside the bootloader, right? So entry.s is the very first assembly file, very first part of the kernel, which is executing on this machine, right, during the boot sequence, because the bootloader just jumped to this, right? So essentially invoked a function, invoked an entry function of the kernel, right? And here is a little bit of magic here, and I recommend you to understand what's going on here. So the kernel itself is compiled to be at virtual address, which is at 2 GBs plus 1 MBs, right? And here we're converting from this virtual to physical address by subtracting 2 GBs, right? So this macro does it, right? And you start here will actually be address at around 1 MBs, right? Because if you subtract 2 GBs from here, you will end up with something like 1 MB, right? 1 MB plus some small delta, and at which the entry point was actually at which the entry point is located, right? So, but nevertheless, so this is the entry point in the ELF file. So it's just the linker uses the start label by default to set it as an entry point. And there is inside the kernel, there is a real entry point, which you as a designer said, okay, that will be the first label which will be executing inside the kernel, right? And so what you're doing here is you say, I will be setting up the page table, right? I don't want to deal, I want to enable paging, right? And I don't want to deal really with 4 kilobyte pages because right now it's not necessary. So I can use just a handful of big 4 megabyte pages, right? And that's why you're enabling here a 4 megabyte paging extension, right? So you reading control register 4, CR4 into EAX register, setting the flag, which enables this sized or 4 megabyte page tables, and then writing this register back into the control register 4, right? That's okay. So you enable this 4 megabyte paging extension. And now you say, look, this is the world. This is how it looks like. So this again, segmentation is enabled already, right? Remember, we did a long jump into a segment, right? So this is the bootloader. This is the stack on which we're currently running, even when we jumped into the entry point of the kernel, which is this start label, right? We're still running on the same stack because we didn't change the stack, right? And the kernel is loaded. Maybe I'm like, there is an extra 0 in my drawing, I should fix it, right? but this is exactly 1 megabyte mark, right? And so the kernel, this is the kernel text here, and the kernel data will be here and everything, right? Because we loaded all the sections, not just the loadable, right? Like in the homework, we actually loaded them all, right? So it's just that some of them, like BSS, for example, might consume 0 space on disk, right? That's why we padded them with 0, right? That's it, right? So now we want to construct a page table, and we have a specific reason for that, right? Here's just a quick recap of the fact that with the x86 hardware supports both 4 kilobyte pages and 4 megabyte pages, right? And I kind of try to recap what it means, but it means that there is only one level of translation, right? So this entry in a page table, right? If you take the virtual page number from the address, this top 10 bits, right? The other 22 bits will be an offset within a page, because the page itself is 4 megabytes, right? And you need 22 bits to address any byte within those 4 megabytes, right? And so there will be no pointer to the next level of a page table. Instead, this is an actual physical page number, which is kept inside the page table, right? So you got the recap, right? Are there any questions about it? All good. And so what we're doing here, so let me ask you a question. Where do you think this page table is coming from? So where we will get it from? Will we allocate it somewhere or what? Let me just disable. Sorry. To disable Slack. So who can tell me? So this variable, the page table, right? So what I'm trying to ask or trying to explain you is this: the page table is inside the kernel data section, right? Because why not? I mean, you can play games like we played the game with the stack and just pick any random address in memory and say, okay, the page table will be there. But this is a little bit awkward, kind of uglish, right? So it's much more convenient to have page table itself as in a data section of a kernel. So for example, we can put it somewhere over here, right? So if this is the, if this is the data section of a kernel, so the page table, this entry free page dir can be just here, right? So how big it is, how big it should be, do you know? Who can tell me the number of bytes? Anyone is following? Yeah, 1024 entries. And in terms of bytes, how many bytes? Each entry is how many bytes? 4 bytes, right? So it's 1024 multiplied by 4 will be 4096 bytes, right? Okay, cool. But this is exactly what we're doing. Again, we're playing this magical trick here. So no, like I will ask about it. Like I will ask the meaning of this macro, right? So why is that? Because the entry page here, everything is linked. The kernel itself is linked and relocated to run at around 2 gigabytes plus 1 megabyte. That's why if you do the obj dump, all the symbols will be in this range, right? So if this is the 2 gigabyte split. But right now, the kernel is loaded actually at the first megabyte, right? Because this is where we loaded it. This is where the bootloader loaded the kernel, right? You will understand in a second. So this is 1 megabyte mark. This is 0, right? And there's a huge address space in between, right? So we say, look, since the hardware itself, we know where the physical address of the entry page directory will be. So if this symbol is pointing somewhere over here, if we subtract just 2 gigabytes, we will exactly land on the physical address of this symbol. So this is what this macro is doing, subtracting these 2 gigabytes. And what this whole thing is doing is essentially loading it first in the EAX register, and then from the EAX register into the control register 3, which is where the hardware expects to find the root of the page table, right? So, okay, so far so good. We say, look, why are we doing this? That's the first question which we might ask. Remember, I mentioned it a couple of times in the past. Our end goal that each process which we're going to be running on the system will have its address space split in two halves, right? So right directly at 2 gigabytes, right? The lower part will belong to the user program, right? So essentially we'll load the process, the text section of the process of the application, data section, like we'll keep some space for the heap, we'll keep some space for the stack, right? And the kernel will be using the second half of the address space, the upper 2 gigabytes, right? It's convenient because you can do the system calls like this without switching the page table, right? But right now the kernel is loaded at address 1 megabyte, so somewhere over here, right? Right now kernel is sitting here. So if you say, look, I will build the mapping like 1-to-1, right? It will be sitting right exactly in the part which we want to be used by the user processes, right? That's why we essentially will create a page table which will map the physical addresses from 0 and up into with a shift. So essentially it will be mapped from 2 gigabytes and up here, right? Then in a virtual address space, the kernel will show up somewhere around here, right? And then we can use the lower part of the address space for the user, right? Okay, good. So that's why we need a page table. So essentially we will create a page table which creates these two mappings, right? Right now, again, the world is like this. Kernel is sitting at the lowest first megabyte, right? Like roughly speaking, above this is the first megabyte mark. And we kind of can guess that the kernel is smaller than 4 megabytes, right? Because we know that the x86 kernel is relatively small. So we say, look, okay, we will create a page table which will contain only 2 entries. It will map the first 4 megabytes and the 4 megabytes at the 2 gigabyte mark, right? Just to get started, so the kernel can show up in those addresses and we actually can enable paging and jump into those addresses and start executing here, right? Although in physical memory, it will be still here, right? Because we don't move anything in physical memory, right? So we want to create 2 entries. So let me ask you a simple question. So why can't we actually, why can't the bootloader load the kernel at the 2nd gigabyte here? And I asked you already the last time, right? Who remembers the answer? CPU isn't in real mode, so the address is too high. It's actually in real mode. It's we switched from real to protected mode, right? So protected means we enabled segmentation, and we can address everything from 0 to 4 gigabytes, right? But Surya is right. So Surya says, okay, look, maybe our machine has only 512 megabytes of DRAM. So there will be no physical DRAM like at the 2 gigabyte mark. So that's why we were doing the bootloader trick. We loaded the kernel somewhere where we know there is still physical memory. So we know that we assume that there is still physical memory about the first megabyte. If you really try to boot this on a machine which has less than 1 megabyte of DRAM, everything will crash, right? But just for practical assumptions and just to simplify the code, we say, look, we believe that at least there is like 234 megabytes of physical RAM. That's why we loaded the kernel here in physical addresses. We can address all addresses from 0 to 2 gigabytes, right? In protected mode, right? Because we're running in 32-bit mode of execution, right, already. So we ran in 16-bit mode for just a couple of instructions when we just started from when the BIOS passed control to us. And this is the convention, because back in the days, the operating systems were not required to support even 32 mode of execution. So newer bootloaders like grep will switch into protected mode and will start the kernel in the protected mode, right? But back then, like for backward compatibility reasons, it was making sense to start from a real 16-bit mode, right? Is there a reason why we map kernel to 2 GBs to 4 GBs instead of 0 to 2 GBs? There is no real reason. I believe that there was some kind of a historical reasons. So for example, so if you do some kind of a emulation mode where you say, I will run a legacy program, which assumes that it has to run at this 0 kind of address range, then the kernel can hide at the very top. But technically speaking, at this point, if you start a clean slate operating system, you can play around. And in fact, the kernel which we built most recently loads the kernel at first megabyte and just leaves it there, and the user uses the upper half of the address space. But I believe there are some historical reasons, although I cannot name them like right off the top of my head, which require this backward compatibility, reserving the lower part of the address space for the user. Okay, nevertheless, we need a page table. So 2 entries, right? So one will map virtual addresses from 0 to 4 megabytes. This is 4 megabytes. Actually, to be honest, look, this is enough zeros. So if this is 4 megabyte, then this is 1 megabyte. So I was right with the amount of zeros, which leads me to another thing. I'm probably missing a 0 somewhere else in this boot main for whatever reason. You want to double check real quick which 0 I'm talking about? Let's just do it real fast. Projects x86 public vim. We're looking at a boot main file, bootmain.c, and it was allocating the scratch space here. So elf header is here. Okay, I got it. I got what we're doing. Okay, sorry, I confused you. So the scratch space is actually here. So it's not at the first megabyte. It's roughly at the 64 Python. It's OX 10000, right? It's roughly at 64 kilobytes. This is where we are reading the elf header, right? Because we know that the kernel itself is linked, right? So the kernel itself is linked to run at the first megabyte. The address, which is in hex, looks like x1000000, right? So exactly those, oh, hold on, too many zeros again. 3 zeros and 2 zeros, right? 2 zeros and 3, so 1 is missing, right? So, but we were saying, okay, we're first gonna read the 4 kilobytes, 496 bytes of the elf header from disk. We're gonna read in a different scratch space, so it doesn't get overwritten. So if you would read it here, then you would immediately overwrite it with the kernel binary, right? Because the kernel binary, all this ph adder, those addresses will be pointing to the locations around the first megabyte. That's why we were doing it. So we read the elf header at a different location to avoid it being overwritten by the kernel itself, right? Okay, just sorry, I didn't look at it like every year, you know, I keep forgetting what was happening. So, and I got confused. Okay, so here, just back to this story. So 2 entries, entry 0, right? Why is entry 0? Because we really want to map physical addresses, and this physical addresses will have the physical page number of 0, right? It will be 0 entry in a page table. We want to map them to, no, yeah, hold on. Get confused too much. Okay, what I'm saying here is that virtual page numbers, which correspond to address from 0 to 4 megabyte, or this will be an entry 0 in page table, right? Because this is how we translate. So we take the address, right? Imagine we have some move instruction which uses some adder, right? And saves it into like EAX register, right? We take this adder and we split it. Normally we would split in 10, 10, and 12, right? But here we will split in 10 and 22 because 22 is an offset. And this 10 will be virtual page number, right? So, and this virtual page number will essentially specify which entry in the page table we have to pick. So we have to pick entry number 0 for addresses which range from 0 to 4 megabytes, right? And for addresses which range from this address, which is 2 gigabytes to 2 gigabytes plus 4 megabytes, right? This virtual page number will be actually 512. So if you take this address and split it into 10 and 22, you will observe that like this will be 512, right? Okay, so how to construct this page table? Does anyone know how to define it in C, for example? It's not as hard, to be honest. This is kind of the beauty of C. C is actually quite well designed, but you can use any other language as well. So you say, well, I will create an array, which I will call entry page dir. It will have 1024 entries, right? Not surprisingly, right? You need to have, because hardware requires the page table to be aligned in a page boundary, right? So C has this align attributes, which allow you to align a data structure at a specific boundary. So this is a page size, which is 496, but sometimes in your probably professional life, you'll be able to use the same attributes to align data structures at a cache boundary, right? So if you are in my architecture class, and we just spend a ton of time on importance of caches, this is the way to make sure that those entries in the hash table or pieces of metadata, like in the graph, for example, data structure, are aligned in a cache line boundary. So you would put something like 64 here because the cache line is 64, right? And this array, you say, look, I don't care about any of the entries, right? I only care about entry number 0. So I will initialize it with the physical page number of 0, right? Remember, the entry will look something like, it will have a physical page number and then flags here, right? And these are just OR. So essentially you say, I will set a page present flag, page writable flag, and page size, meaning that it's a 4 megabyte page, right? Don't look into the next level of a page table. The next entry will be page itself, right? And the second entry is this 512 entry, which we just talked about it. And again, since it maps to physical address 0, physical page number 0 will be here, present, writable, and size, right? To make sure that we're going through a 4 megabyte page. Okay, got it. So we did it, right? Define the page table directory data structure. And I just go in details, right? Again, where is it located? It's located in the data section of the kernel because it's just an array. So the compiler will put it in the data section. The table itself is 4096 bytes. It has only 2 entries initialized, entry number 0 and entry number 512, right? And if we load it in the hardware by writing into CR3, that's what we did before, right? CR3 will be pointing to this page table, right? If you like, the pointer will go right here, right? And this page table, we haven't yet enabled paging, right? But the moment we will enable paging, our virtual address space will contain only 2 mapped pages, right? The page which goes from 0 to 4 megabyte, and the page which goes from 2 gigabyte to 2 gigabytes plus 4 megabytes, right? So each of those entries, they are not drawn to scale, are 4 megabyte regions, right? But both of them map to the same physical memory. So this is the region of physical memory, which ranges from 0 to 4 megabytes, right? Here we're just mapping with the shift, right? Which means that the kernel will be mapped twice. It will be mapped here and it will be mapped here, right? Right? Got it? And of course, since the linear doesn't change anything, it will appear here as well, right? But the kernel is saved only once in physical memory, right? So this is physical, right? Okay, so now let's turn on the paging. So the flag is inside control register 0. So again, we read the control register 0 into the EX register, set up a couple of flags which enable paging, right? We do the OR on this register and then write it back into CR0, right? At this point, the next instruction will be executing, essentially we switched, it will execute, it will require the page table. It will first do the logical to linear translation and then linear to physical, right? So if we wouldn't set a page table correctly, this instruction will crash, right? It would crash. Let me ask you a question, a tricky one. So why did we map this kernel twice? Okay, it's maybe too early to ask this question. Okay, let me just go ahead forward, and I will ask later, but keep it in mind that I will ask. Okay, now we want to switch to a normal real stack, because up until now, we are using this kind of ad hoc stack, which we created here, right? Just below from 7C00, but we say, why don't we use some stack which we allocated in the data section of the kernel, right? So it will be mapped twice, of course, here as well, right? And we say, look, we just create a variable which will have a name stack, and we know that it's a kernel stack size number of bytes, so it's 4096, right? And so essentially we load it in the register ESP. You say, look, what about this old stack? This old stack is still staying there, but we'll never use it again, right? We just use it for a little bit inside the bootloader, but now we're just done, and the kernel will run on its own stack, which is like, which we provide inside the kernel. We'll create more stacks as we'll go forward, but this is the first stack on which the kernel is running, right? Okay, got it. We did this. So this blue is this new kernel stack, right? This one is still here, but we no longer use it, right? It's not necessary, right? The old stack, the data is there, right? But this is in the data section, we have the stack variable, right? And now we're ready to jump to main, right? That's in the end, this is our goal. So what we're doing here is we're loading the main into the AX register and then doing an indirect jump. So the ad hoc solution, which why can't we just say call main, right? So for whatever reason, despite the fact that we've seen that if main is not a static function, it should actually be invoked not through a relative jump, right? Not a relative jump. So it should have been like using a real address, right, of main. However, maybe it was like that in the past when the compiler was generating relative invocations for local functions, right? And of course, then the address of main is a relative delta, right? Which would be something like, okay, maybe it's like 527 bytes up or down. You can start executing main, right? But that's not what we want to do. What we really want to do, since main itself is a symbol, which is somewhere in the second gigabyte plus some delta, right? Or second gigabyte plus first megabyte plus some delta, right? Because this is where we linked and loaded the kernel, right? This is how the kernel is compiled. It works with those addresses. We have to jump to this address, right? So that's why we write this address, which starts with X8 and then goes to something like 010 and then 4 zeros here, right? So because this is the second gigabyte and this is the first megabyte after that, right? So plus some numbers, A, B, C. We want to jump to this address. That's why we just load this number in the EX register, waiting to do the relative jump, and it's jumping to this address. So it doesn't create a return address on the stack, right? The stack is still empty. So which to a degree, you might say, okay, did we break the calling convention? A little bit, but we don't really care. Why is that? Because we are not passing any arguments to main, right? If you would pass an argument, that you would have to push some dummy address on the stack, right? To make sure that arguments are properly aligned on the stack with respect to the stack pointer after the invocation, right? But the main is a void function, so we don't really pass anything inside. So we jump here and we land in main. And finally, we find ourselves in this wonderful main.c file, which is like use the power of C now. You don't have to think about assembly anymore. So you boot it into main, right? And this is your current or next homework, right? Essentially, boot into main, right? Are there any questions about how we did it? How we got to main? All good? All clear? So if we are good on this, then I switch to the next slide deck and I will start talking about what's going on in those functions, right? Okay, let's do it. Yep. .238p. So we start executing inside main. And since we just finished, we don't really have to do a recap, but essentially we need to understand what is the outline? So what is it we want to do here? So what do you think the kernel should do, right? So this is the overview. So this is how we were advancing through the boot sequence, right? Like the bootloader. So essentially, this is the bootloader. Right? And this is the kernel. We just done it, so we don't. There's no need to recap, right? But what do you think? What do you think we're gonna be doing? This is the world. This is how it works, right? And this is where we're running in main, right? So the question is which I'm trying to get to is what's next. If you were writing this kernel, what do you think you're gonna be writing inside the main?
Signal handlers.
Signal handlers.
I mean interrupt handlers. Signal handlers.
Yeah, excellent idea. So we want to set up interrupt handlers. What else? You probably were working on embedded systems because this is what, embedded system developer is like. It's a nightmare. We have to set up interrupt handlers and everything else is kind of like, doesn't really matter. But imagine you're building a normal Linux-like kernel. What do you think you're going to be writing? What's the end goal? Remember, we talked a little bit about it. We want to run something like shell or GUI, which means that we kind of want to run processes, right? So we want to run processes, right? Because that's shell and GUI are all processes, right? We want to get to be able to run processes, which means that, okay, we want to like load ELF files from disk. This from disk means that we need a file system, which we will cover at the very end of this class, right? So, and we need some mechanisms to essentially start a process, which means that I kind of need something like exec, right, style system call, right? So this interrupt handlers will also enable system calls, right? So kind of protected entries into the kernel. Yeah, so Dominic, you're right. So he says, and goal is to run a user process, correct. So, and this exec essentially says, look, for each process, if I ask you a question, what is a process? You will probably say, look, I don't really know first, and that's an honest answer, but process will be a very small data structure in x86 kernel, which will fit on one screen. But roughly speaking, it's some in-kernel state, kind of like a file descriptor table, right? FDs, like which keeps track of open files, maybe some other state, but really it's also a page table because each process will have its own page table, right? And in order to load something in memory, you have to construct those page tables. So the very first thing, even before setting up interrupt handlers, it's okay to delay it because remember we disabled them. So the bootloader disabled and the kernel, this is the convention here that kernel trusts that the interrupts are disabled for now, right? So before we doing that, we want to learn how to construct page tables. And we don't even have a page table for the kernel. We only have this handicapped page table, which maps only 2 regions of memory. You can't even access all available physical memory. You can only access the first 4 megabytes, right? But other memory here, there is no address you can use in the register because this is unmapped. So this will result in a page fault, right? That's why you say, look, I have to construct a page table, which at least covers the entire physical memory. And then I will learn how to start processes, set up interrupt handlers, and we'll boot into shell eventually, right? We first boot into main. Now the goal is to boot into shell, right? So, and it will take us the rest of this class to boot into shell, to be honest, right? Kind of like we'll get there faster. But you probably get the feel of it, right? So this is the main tasks, right? So again, I'm trying to demystify the act of building operating system. So it's kind of, again, fits on one slide. This is that's what you want to build initially, right? And it's good enough even for like if you're running embedded system, or even if you're running something like Intel management engine, you know, you can boot x86 there probably, as long as Intel can give you access. It's not super hard, right? But yeah, but that's about it, right? So let's start on this route. So again, my end goal, yeah, run processes, right? You would like to make sure that they are isolated from each other and they are isolated from the kernel, right? And the way we achieve, again, isolation, we ask a question. So what is a process? And as I just was saying, okay, it's some state in memory, right? So there will be code of the process, stack and heap, some in-kernel state like open file descriptors, network sockets, which we don't have here in x86, but we have pipes, right? So processes can communicate with each other, right? And since processes cannot trust each other, right, we want to isolate them from one from another, right? If they would trust each other, we would just be loading them in memory. Remember, no segmentation, no paging, just load the text and data section, create some stack, and that's okay. That's from address 0. If you want to run the same process again, just relocate it and put it somewhere else in memory, right? So just put it at address ABCD. And since you can relocate, if you have enough relocation information, this thing will run, right? Why not? It's just fine. It's just the problem is that this process can easily access the memory of every other process in the system, right? That's why we want to build some boundaries between them. And we know that we can build those boundaries with segments, but it's much easier and more flexible to build them with page tables, right? So, and that's why we want to learn the page, like how to build the page tables. And this is actually, if I was kind of like imprecise when I was talking about the layout of the x86 process, but this is the real layout of the x86 process, right? So x86 loads the program text section at address 0. Above this, I mean, you don't really know whether it's a text or data, but the process is linked to run at address 0, right? And it so happened that the text section is first and the data section is second, right? Then above it, there will be a guard page to prevent stack overflow, right? So there will be a guard. And above that, there will be just one page of stack. And above this one page of stack, and x86 doesn't have multiple threads, right? So we will do a homework on enabling multiple threads of execution in x86, right? But above there will be like first free space, but there will be heap, which will be growing towards the end of the address space. And the second part of the address, the second half of the address space above the second gigabyte will be used by the kernel, right? So now this is the exact picture how x86 will be doing it, right? But you don't have to spend a ton of time right now thinking about it. I'm just saying that this is the first time when this slide shows up and it's correct. The goal again today is to learn how to build the very first kernel page table. The page table itself, remember, will map the virtual addresses inside each process to some physical memory, which operating system will be allocating for this process, right? Because physical memory is also like a limited resource. So some pages are still available, but some are taken, right? And some will be taken by the kernel itself, right? And some will be taken by processes, right? So operating system will keep track of which page belongs to the kernel and which belongs to one of the processes, right? As I was saying, it's not strictly necessary to map the kernel on top of the address space, but it's still much faster in terms of system calls. And the only reason not to map the kernel today is to protect against the meltdown attack. But again, only people who are taking the architecture class or people who can like reason about it can understand what meltdown is, right? Like again, you can watch either my lecture, mine is pretty good actually. So on meltdown from last year, or wait until I will get there this year and you will get an explanation for the meltdown, right? So again, I recommend doing that because meltdown is probably every other computer security article mentions meltdown. So you at least have to understand what it means, right? So either join us for the architecture class, so I will send a link, or just watch a recording. Okay, so but that said, okay, how we achieve isolation between processes, we'll say, okay, each process will have its own private page table. The operating system will be switching between them by loading CR3, right? We know that CR3 contains the root of the page table. We'll cover the context switching details, right? In this pink address space, essentially, all the pink pages are mapped to some physical pages which belong to pink process, and pink and yellow and pink and green will never overlap, right? One question which I didn't explain is that since we're using the same page table to map both green and yellow, how do we achieve isolation from green to yellow, right? Why can't the green, for example, just do this write or read of yellow memory? And a page table, remember, it has a special bit. Like each entry in a page table says, okay, whether this entry is accessible from privilege level 3. And the user will be running in privilege level 3, and essentially all the addresses which user can access will have to be set. The bit has to be set. We'll have to set it to user accessible. Otherwise, it's a protection violation and again exception, and then the operating system will likely terminate the process, right? So again, hopefully it's like you have some intuition about it, but we'll come back to this later, right? So don't worry about it. So again, our goal is to build this address space. So the lower part belongs to the user, the upper part belongs to the kernel. Right now we have an address space, like a page table which maps 4 megabytes from this region and 4 megabytes from this region, right? And nothing else, and everything, both these regions are mapped to the first, like this is 4 megabytes. It's better to draw it this way as a square. Which are mapped to the first megabytes of physical, right? So I assume that you remember this still from 10 minutes ago. This is the world, right? This is how it looks. And really the kernel, which we loaded at the first megabyte, sits right here in physical memory, right? There is some free memory above it, right? Because the kernel itself is less than 4 megabytes, less than 3 megabytes even, right? If you start from 1 megabyte here, right? There is some IO space, something like some memory below this 1 megabyte is used to communicate with IO devices, like a frame buffer is there for VGA, and some other, like you can access other interfaces if they're like other hardware devices, if they are present on your machine, right? So, and our page table itself contains only these 2 entries. So one entry maps this area and another entry maps this one, right? And all the addresses are here correct. So this is 0, this is 4 megabyte, this is 2 gigabytes, and this is 2 gigabytes plus 1 megabyte, and this is 2 gigabytes plus 4 megabytes, right? Okay, so the physical address space, we assume that we're booting QEMU on a machine which has 512 megabytes of physical memory. However, x86 will only use physical memory up to this constant, which is called physstop, and which is roughly 234 megabytes, right? So it's roughly here. So x86 will never use this memory, which is wasteful, but it's okay. It's just a teaching operating system. There is also one tiny bit here of the address space, which is at some point, hardware designers ran out of addresses below the first megabyte, and they said, okay, there are so many devices that we need to reserve some fraction of this physical address space to be an IO space again. So what it means is that really, if you have only 512 megabytes of physical memory, if you do a write into this region, the controller, remember, again, below the last level cache, so if this is the core, and it sits on caches like L1, L2, and this is L3, below last level cache, there will be memory and a PCI controller, right? And a PCI controller. And those guys are picking up the idea that, okay, there is no physical memory which backs up this address. So rather we have to send a PCI transaction, and there will be a packet which goes on the bus and reaches a specific device, right? And if you have more physical memory, if your really machine has 64, maybe gigabytes of physical memory, then this tiny hole, like you just wasting this amount of physical memory, you cannot use it, but just because when you issue a read or write, it actually goes to the PCI device, right? Instead of going to the memory controller, right? That's how it works. Okay, any quick questions about it?
The IO space, is it in physical addressing? This is physical addressing, right? 0x.
Right, correct.
Okay. And one more question, like the user process in x86 can only utilize 2 GB of program address space.
Right, in x86, correct.
Is it the same in like real, like other Linux, like operating systems?
In Linux, the split was different. So on 32-bit machines, the split was at the 3 GBs boundary for that very same reason, because you say the kernel doesn't need that much virtual memory. So 1 gigabyte is okay, and the user can use 3 gigabytes.
Okay,
right?
and the compiler has to make sure that everything, whatever you're doing, is fitting in that.
Yeah, but compiler, it's very rare that the binary which compiler compiles is larger than a couple of megabytes, right? Because if you allocate a lot of like global variables, you're doing something wrong. So really what this space is usually consumed by is the heap, right? So essentially you keep allocating dynamically on the heap, calling malloc, or doing just like a new operator in Java or C++, right? So that's a typical like programming discipline. So typically we avoid doing large allocations in the data section, because you also will use space on disk, right? So like a couple of gigabytes of disk space just to save some. Do you really have this data? If you have this data, you should put it in a file and read it dynamically, right? If it's something like a genome, a human genome, for example, right? So just keep it in a file, not inside the data section of a program, right? Agree with this?
Yeah. One more quick question. That IO space, right? It has to be somewhere. The virtual address has to be mapped to this. Like, so suppose I'm assuming a process will write to some memory address, and that
Absolutely.
will translate.
Right. This is where we're getting. So right now you can only write into this IO space because this guy is not mapped anywhere, but we're going to map it here. The kernel will map it to make sure that it can use a virtual address which gets translated to this physical address.
Okay.
Because you simply cannot issue a physical address without going through the levels of the translation, right?
Yeah.
There's no way to kind of like magically switch it off and switch it on again. So it's always on.
Got it. Thanks.
Okay, cool. So this is the address space, right? So what we want to do, this is the outline for the next 25 minutes. We will first create a kernel memory allocator, right? Why do we need a kernel memory allocator? Because we need memory, like in order to construct the page table, right? You need memory for those levels, right? And for the very first page table, we got it in the data section. It's okay, it's only 4 kilobytes. We can do it once because we did it before allocator was even on, right? But for those, like, we need to allocate those guys dynamically, right? So each process will have its own page table. And so we don't really know how big it will be, right? So every time we need a new page, we say we need something like page alloc primitive, right? Which will go like an allocator, which will keep track of available physical memory, right? And we'll be saying, okay, look, by the way, you need a new page, I'll give you this one, and I will mark it as used. You need another one, I will give you this one, and I will mark it as used, right? And then maybe later on you will deallocate it, I will add it to my pool, right? So kind of an allocator, right? Like a regular memory allocator. It will be just allocating objects of one size, 4,096 bytes, right? Agree with this? Okay, let's build this allocator. It's called the kernel memory allocator, right? So you may ask a question. So why don't we continue running on this 4 megabyte page table, right? And it's okay, you can do this, but imagine really you're running processes like shell, or even WC. The text section of WC is less than 1 kilobyte, maybe 1 to 2 kilobytes, right? And you say, look, but I don't, if I create this process, I immediately wasting the 4 megabytes just to like map this tiny 1 kilobyte of text section, right? And you say, no, that's probably not a good idea. Let's waste that smaller amount. And you say, instead of using 4 megabyte pages, I will be using 4 kilobyte pages. That's why the kernel wants to construct a 4 kilobyte page table. A more advanced solution would be mix and match, essentially doing something like map the kernel part of the address space with 4 megabyte pages and map the user part of the address space with 4 kilobyte pages. And I assume that the modern hardware, actually 64-bit hardware, definitely support this mode of execution where you can mix and match pages of different size. I assume that 32-bit hardware does the same, but this version of x86 kernel doesn't do that. And there's minor probability that I'm wrong and that 32-bit version of x86 doesn't support it. We can double check, right? Okay, so our goal is to construct a page table which has 4 kilobyte pages, right? So our primitives will be alloc and free, right? So essentially to allocate pages for page table, we're lucky that the stack which we'll be using is also 4096 bytes as well. So it's very convenient. We can use the same allocator which returns a page, right? And you will see later on that x86 actually doesn't allocate data structures. So some you will only be allocating pages. Like there is no malloc inside x86. Malloc which allocates objects of small sizes, like something what is like 64 bytes, for example. You will see why, because everything is statically allocated. Maybe it's an array of processes and you keep track of which one is available, which one is not. It's kind of like a very primitive allocator, but you will see how it's done. So, but if you ask a question again, how this allocator can look like, do you have an idea? You want to keep track of available physical pages. And I will ask you, okay, build me an allocator. What will you build? A linked list. Yeah, excellent idea. Actually, this is how x86 is doing it. It's a funky linked list. So x86 will say, look, I will have this variable which will contain the head of the linked list. It will have a pointer to the next element of the list. And this next element will be within the page itself, right? So it will be within the page itself, and it will contain the pointer to the next element on the list and the next element on the list. So it's not like two linked lists. One is living somewhere over here, having pointers into, like they will have pointers like this, and those guys will have pointers to pages. So the next element of the list lives within the page itself. It's just a simpler organization. There are pros and cons, right? So pros is that it's a simpler organization. Cons is that you will see later in a little bit, right? But I'll explain. So what this data structure, which sits in here, it can be this just structs. Why is it run? Not sure, but it can be just next, essentially. It's one next pointer, right? So one 32-bit pointer, 4 bytes. That's about it, right? We don't need anything else. And your alloc operation will be just simply taking a list which was pointed by the head, right? This pointer used to be pointing right here. So this returned by the allocator, and essentially allocator will be pointing to the element which was pointed by next. Very simple allocation. And the allocation is a reversed operation. So you can allocate a couple of those elements, and maybe you can deallocate one. So you say free P, right? And at this point, you add this element back to the list. The head will be pointing to this element, right? This line, and this next will be pointing to the previous element on the list. So here's where we'll go back here for a second. This was the state. You deallocate this pointer P. This is how the state changes, right? Kind of very, very simple linked list. You say, sure, like this is my allocation. So you say I'm assigning R the head of the list. If R is not null, I will take next and assign it to the free list, and then I will eventually return R, right? And similar K free. So you take element which you are deallocating. You say, okay, I will assign it to a temporarily variable. I will set R next. So this is R. R next will be set to whatever this head was pointing to, and I will update the head to point to R, right? Again, super, super easy. Is it clear how it works, this allocator? Okay, good. So the question is, where does this memory comes from? Any ideas? There is one wrinkle here. Since we said that the linked list itself doesn't live within the kernel, but lives within the page itself, it means that this memory actually has to be mapped by the page table, right? If it's unmapped and you try to write into this memory, it will be a page fault, right? Agree with this? So you need to find a little bit of those pages which are mapped. So where do you think you can get them?
In the page table itself?
Page table itself, hold on. Page table itself is, our page table is in the data section of the kernel. It's only 4096 bytes. You need more pages to allocate new page tables, right? So x86 does the following trick. It says, look, I know that I mapped the kernel at the first megabyte, and I know that the kernel is relatively small. It's actually less than 1 megabyte, right? So there must be some empty area here, free space from the end of the kernel to the 4th megabyte, right? Agree with this? This is this free memory, which is above the kernel, and it's already mapped. So the question is like, why not to use this memory? Why not to splice it in those chunks and add it to the list? And this is exactly what x86 is doing, right? You got the point how it works? So you can create a symbol. You can tell the linker, please create the symbol at the very end of my last section. And there is a little bit of a linker magic, but you can understand it easily if you look through. And this end symbol is actually this. It's 1 megabyte. You can put this into Python, and you will learn the actual size of the entire kernel, right? Tags, data, BSS section, everything, right? And all this memory, which is from here to the end of the 4th megabyte, is actually free. So I'm using the addresses which are in the 2nd gigabyte range because we jump to them, right? So it's from the 2nd gigabyte to the 2nd gigabyte plus 4th megabyte, right? Okay, so why not to initialize this list of empty pages first? Because there is more physical memory. So we will do it in 2 stages. First, we will just initialize a little bit of those pages. Then we're using those pages. We just believe that there will be enough pages. We'll construct the very first page table, which instead of just mapping 2 areas of 4 megabytes, will map more memory in a more meaningful way. I will explain what we're going to map, but we will map all available physical memory. So, and then we can use that all available physical memory in a very similar manner. We'll add it to this list, and then we will essentially, the kernel can operate and allocate all physical memory, right? Because it will keep track of all available physical memory, right? Okay, sure, let's do that. So the very first function which the kernel execute, it initializes this kernel memory allocator. There are 2 stages, Kinit1, and there will be Kinit2. And this first thing essentially says, I will actually initialize the memory allocator starting from the end symbol in a kernel and going to the 4 megabyte, which we translate from physical to virtual, roughly speaking, adding just 2 gigabytes, essentially 2 gigabytes plus 4 megabytes, right? That totally makes sense because we know that this area is actually available, right? So Kinit itself is a very simple function. It takes 2 arguments, virtual address start and virtual address end, and does something what is called a free range. So kind of like it will be freeing page by page, but free operation as the page on the list, right? Which is kind of cute because you don't have to write a different initialization procedure, right? You see, I'll just deallocate those pages like I pretend they were allocated before, and act of deallocation will put them back on this list, right? Which is nice. So free range is very simple as well. So it will be just saying I will round up this variable. So end might be in the middle of a page, right? So I will round it up to make sure that I will start from the next page from P, and I will be going from P, and I will be incrementing P by the page size. P is a char pointer, so it just increments by 1 normally. So, but you can increment it by any number, right? So by the page size, and I will be going up until the end, right? And I will be incrementing P by the page size, and I will be freeing those elements, and each free will put 1 page on the linked list, right? Okay, that's very simple, very intuitive, right? And just spending time here so to make sure that you understand, I mean, those are the lines, you have to read them actually and understand the source code of the kernel, but this is what I'm encouraging you. I'm explaining what the source code is doing, so you're not frightened anymore. You can actually go ahead and read it, right? Okay, we did it, right? So how do we get this end? End is defined as this extern symbol. So it's not defined by your program. It will be provided by the linker, right? So linker can do this magic. It can say, look, I will provide the symbol. right? And this is your way to connect to this symbol, right? Okay, we got it. So this is the state of our system after we donated the pages, right? So this is the beginning of the 2 GB plus 4 MB, and this was mapped by the entry in our 4 MB page table. That's why we can read and write those elements, right? Updating them as we go through the linked list. Okay. Now we have a memory allocator. It has a little bit of free pages, which we now can use and allocate to make sure that we can construct the page table out of them. Okay, our first goal here is to actually construct this page table. How do you think we will construct this page table? Do you have an intuition for that? So how can we build this, something like this? Any ideas? Struct. Yeah. The page table will be a struct, I agree. We can represent it as an array of 1024 entries, right? But what's the high-level algorithm here? I kind of say that the high-level algorithm is to allocate the root of the page table directory. And then if you say, look, I want to map a specific range of virtual addresses to a specific range of physical addresses, every time I will do the mapping, I'll say, I have to add it to the page table, right? And it might be two outcomes. Maybe the next level was not yet allocated. Then we will first allocate this next level from the allocator, and then we will patch up all the entries to correctly make sure that this mapping is correct. And then you go forward, you reach the next page or reach the mark of the 4 MB, right? Because you filled in all the entries here, and then you allocate the next level again, right? So at a high level, it's just kind of like a giant loop, which says, okay, which virtual address I'm mapping to which physical address. If I have a page table directory and a page table, then fine, I'll just update the entries with flags. Like we just did it already. Like we initialized this 2 entries, right? We just put a physical page number into the entry, right? Plus some flags. We'll do the same here. So intuitively, looks simple. Okay, let's take a look. So this is the second function, which creates the very first 4 KB page table in a kernel. It's called kernel virtual memory alloc, right? Okay, let's take a look at what it does. So here we need to reason a little bit about what physical memory we want to map where. So I kind of argue that what we want to do is that we want to map these 4 different regions. So first region is IO space. It should be readable and writable. And we want to map it. It starts as physical address 0. We want to map it at the 2nd gigabyte, right at the mark, right? So we were going to be mapping with a 2 GB shift. And this one will be readable and writable, so you can access devices in the frame buffer, stuff like that, right? Then there will be a second region, which we will map as read-only, because this is the kernel, text, and read-only data. There is no reason to map it read-write. It's more secure, safer in a way that you will, if you accidentally try to write into this region, you're not going to overwrite the kernel code and crash, a couple of hours later in some mysterious way. You will just immediately crash with an exception. So it's a good habit to provide those, to construct those mappings with minimal privileges, right? And then the third region is essentially kernel read and write data, right? So readable, writable data like BSS and just regular data section, but which has write permissions, and everything, all the pages up until this constant physstop. So I told you, like, even if the machine has 512 megabytes of physical memory, x86 will only be using memory up until physstop, right? So, and this one will be mapped with read-write permissions. And the final fourth part is this IO space, which again has to be mapped with the read-write permissions, and it has to be mapped at the very top. Why not to map it like 1-to-1 at the very top of the address space, right? Right? So 4 regions, you kind of understand the semantics, and there is nothing else. It's again, it is as simple as this. just 4 regions, nothing else, right? Okay, let's do it. Are there any questions about those 4 regions? Everyone is good? Okay, let's do it then. So let me just go through the outline. As I was saying, our outline is to say we're going to be moving address by address. We say, well, I want to map this physical address, which is 0, to virtual address, which is 2 GBs, right? I first need a page table directory, so I will have to allocate it, right? So if I allocated it already, I know which entry, because I will split this 2 gigabytes into 10, 10, and 12. I know which entry in the page table I need to update, right? So this one comes from the allocator, right? Which entry is this one, by the way? Who can tell me what number? 512, exactly, right? Dominic deserves a couple of points for his final score, but don't you worry, everyone gets good grades anyway. So 512, and roughly speaking, you say, look, I want to put the address of the next level of a page table. Obviously, it's not yet allocated. So what are we gonna do? We allocate it, and we'll patch this entry to point to exactly the physical page number of this page level 2, page table level 2, right? So that's fine. What's next step? Equally simple. You say, look, what are those 10 bits? I kind of say, okay, of course it's entry number 0 because all these bits will be 0 for this page, right? We're mapping to this one, right? And you say, look, hold on, where are we mapping it? We're mapping it to P, right? P is currently 0. So what we will write here is the physical page number of P, which is 0 in this specific example, and then some mode flags like read write. Essentially, if we're mapping this region, it will be read write, so it has to be writable, it has to be present, right? And it has to be actually only kernel accessible, right? Because, by the way, right, we don't want a user to access this page, right? So for privilege level 3, this bit should be clear, right? Okay, so that seems relatively easy. And then we go to the next page. So essentially, we say we started from page number 0. We want to go to page number 1 or this page, right? And essentially do the same procedure. In this example, you don't have to allocate page table directory because it's already allocated. You don't even have to allocate page table level 2 because it just was allocated. And you land magically, if you're going with a 4 kilobyte increment, you land on entry number 1, right? So if previously you landed on entry number 0, right? Here you're landing on entry number 1. And again, you just simply write this entry to make sure that you are writing like this P plus 4 kilobytes or with flags, right? Is this clear, this outline? Okay, all good. So because again, the next homework will ask you to construct a simple page table, right? You're gonna boot into main and I will ask you to construct a simple page table. The outline is exactly the same. So it's just the code which you have to write. And you can actually look at the code which x86 is using and kind of like say, okay, I'll do the same. You can copy if you like, but it's easier to type a simpler version of the same code yourself, right? So just pay attention to this. Okay, so, and this is exactly what the kernel is doing. So the kernel said, okay, I got it. This is the outline. This is the implementation. So this function kv malloc, that's exactly the same. It says, okay, I will first invoke this function, which will create this page table itself, and it returns a pointer to the kernel page directory. And then we will switch. So essentially this switch kvm function will switch from the entry page dir, it will switch to this new, so CR3 was pointing here, CR3 will start pointing to this kp kernel page directory, right? So essentially this function will do it internally. But let's first take a look at this one, setup kvm. So we're currently actually running inside main and we're running inside kv malloc, right? So I'm just providing a backtrace here for you to understand where we are in the kernel, right? So this is what we're doing here. So we say, look, we first need a page table directory, right? For the first root of a page table. So we use this kalloc, which we just created. So this guy goes to the linked list, right? And gets us the page, right? From that list. We we have a type for that. So essentially it's a kind of like an array, right? So we're typecasting to this and returning a page table directory. We initialize it with zeros because it just makes sense, right? So essentially all of this initially will be zeros, right? What we're doing next, we're saying, we're gonna be looping through this something what is called a kernel map. And kernel map will contain some number of elements. Kernel map is essentially a map which contains those 4 regions which we talked about, right? Read, write, I region, read-only memory of the kernel, read, write, free memory, and then read, write, I region at the very, very top, right? But you say like, for each entry in this kernel map, it's kind of convenient. You say, look, I will represent all my memory as an array of the regions, right? And you say for each region, I will be mapping pages. So here you will say, I will, so each entry in the kernel map, K, will have a virtual address. It will have a physical address, right? Physical start, so virtual start, physical start. And it will have physical end and physical start, which will give you the size, right? The size of the region, right? And then the permissions, essentially read, write, maybe executable, stuff like that, right? And then you say like, where are we mapping it? We're mapping it inside this page table, right? Okay, bear with me for one more second. Let's take a look at this function. Let's just take a look first at this kernel map. So the kernel map, as I said, is an array which represents those 4 regions, right? Like read, write, IO space, read-only data, read, write, kernel data, and up until fizstop, right? All this region, and read, write, IO space, right? So what we're doing here, this is the representation of this array. I have a picture here for you to map more easily. So it's an array of data structures. Each has a virtual address, physical start, physical end, and permission bits. And so we initialize the IO space region like, what is virtual start? We want to map it at 2 gigabytes. This is current base. What is the physical start? Address 0, because this is here, address 0. How far are we going to go to extended memory? It's exactly the constant which describes this first megabyte where we map the kernel, right? And what are the permissions? Writable. Same, the next entry, kernel reads read-only data, right? So permissions here will be actually 0, so not writable. So we start from kernel link. It's again symbol which constant which defines at which address the kernel is linked. It's 1 megabyte. We translate it back to physical, right? So essentially kernel ring, it's in the range of 2 gigabytes plus 1 MB, right? So, but we translate it back to physical to get it a physical start. And we are going up until data. So because this is where the data starts. So this will contain text, and read-only data, right? And this is the data section, which is writable, right? So it will be the next entry, right? And so on. So essentially you can see how we can initialize those entries, right? So the last one goes from data to, and the physical end is a fizstop, right? So essentially this constant. And this IO space goes from dev space to actually the end of the address space to 0, right? So it kind of wraps around here. So, but you can get it, you probably got an idea. So it's just an array. So this is, again, this is the example of how you can program those concepts and conveniently represent them. So it's not a mess. It's not like 10 different defines. It's convenient representation as an array, right? Okay, let me stop here for a sec. If there are any urgent questions right away, so just go ahead and ask them. If not, go take your next class and I will see you actually next week then. So let me hang out here for questions.
The kernel doesn't use the same stack as like the kernel uses the same user stack as what about the stack in the kernel?
Right. So right now we're just using one stack. In the end, when we boot on SMP, the kernel will start something what is called a scheduler, right? The thing which will be running on each processor, and each processor of the kernel will use a stack for the scheduler. And then when a new process is created, there will be a user stack, which the user level code will be using. And there will be also a kernel stack. When user drops into the kernel with a system call, it will be executing on this separate stack. So each process will have at least 2 stacks, one in the kernel, one in the user. But it's coming, so don't worry about it right now. But again, I appreciate the question if you're thinking about it. Good. Is xmem equal to kernel link here? No, kernel link is 2 GB plus 1 MB. Oh yeah, actually you're right. And xmem is the same constant. Yeah, should be equal then. You're right. At least it looks to me. But we can quickly grab, again, this is the power of, where is my wonderful projects? No, damn it. I was here. Grab kernel link. And kernel link is defined mem layout. I can make it larger for you. So kernel link is 2 GB, and xmem, xmem is actually, this is xmem. So xmem is just 1 MB, right? So I was wrong. So kernel link, hold on, we were looking at kernel link. So kernel link is kernel base, which is 2 MB plus 1 MB, which is xmem. Got it? I mean, I was wrong, sorry, when I was answering. Right. Any other questions? Okay, then good. See you next week.